Hello, this is Mr. Gilmore with the 11.5 Areas of Regular Polygons lesson. Now we have enough machinery in place that we're going to be able to tackle the areas of regular polygons. Now, in order to get to the area of a regular polygon, we have to remember that regular polygons vary in different sizes based on the number of sides that we have. As small as really a triangle and up to really any number of sides. So we're going to have to figure out a way to generalize our area formula so that it covers all cases of any given regular polygon. Now, how we're going to do this is we first need to start off with a few vocabulary words that we have not seen yet before that involve our regular polygons. So before we get to our area derivation, we must begin with these new kind of objects we find within inside of our regular polygon, and we're going to find that the objects we're going to find that these other properties of our regular polygon is what is going to help us derive our area formula. So where we begin is actually just with a simple uh, reminder of what a regular polygon really is. So remember, a regular polygon has all equal sides, has all equal angles. Remember, we use these two fancy words of saying that a regular polygon is one that is equilateral and equiangular. And so because of this, we're actually going to be able to take advantage of knowing all the sides are equal and knowing all the angles are equal to actually help derive an area formula for any given regular polygon. Now, the polygon we're going to be using as our kind of main template is the hexagon. So we'll see the hexagon show up in every single one of our examples today. And as we begin moving into the generalization, well, again, we'll use it as a template. However, regular polygons aren't always going to be a regular hexagon. So we have to then figure out how do we find the area of a regular polygon based on the number of sides, because that's really the variable that changes depending on what regular polygon you are given. So let me introduce you a couple new components that are involved with the regular polygon. Let's start with what we call a regular polygon's center. So every regular polygon has a center to the circle, or sorry, center to the regular polygon. And this center is a point that is equidistant from all the vertices of the regular polygon, which means this point in the interior of a regular polygon, when we connect that point to each one of the vertices of that given regular polygon, all of those segments produced are equal in measure. Remember, equidistant means same length, right? Same measure. And we want to give those segments a name. So if I were to produce a segment from the center of our regular polygon to any one of the vertices, there's a segment formed. Let's call those segments circumradii, or for single, just circumradius. Now, if you take a look at that word, let's break that word down. Circumradius. Well, we've seen this prefix of circum before. We've used it with circumscribed polygons. We also saw it with circumference of a circle. And as it turns out, a circumradius is tied in with our relationship of a circle, and here's why. We learn that with any given regular polygon, we can inscribe it within a circle. Essentially what that means is that the circumradius length is actually the same length of the radius of the given circle that we can inscribe this regular polygon into. And another thing we can find out is that the center of the circle is the same point as the center of our regular polygon. So in our diagram below, we have point C as labeled as the center of our regular polygon, and we have those dashed segments produced from the center to each one of the vertices of our regular polygon. Those are the circumradii, and you see I've denoted those as all being equal. We're actually going to see that when we approach finding the area of our regular polygon, then in some cases we may be given the circumradius information, and from that we need to find the area of the polygon, which we'll see an example like that at the end of our lesson. There's another segment we need to introduce, a new segment we haven't seen before. This is called an apothem. So if we can produce a segment from the center to a vertex, which is the circumradius, we can also form a segment from the center that is going to be perpendicular to any side of our regular polygon. We call these perpendicular segments apothems. So in the diagram below, we still have that center point C. Again, we use our hexagon as our kind of main template. And from that center, we've produced an apothem. An apothem is that segment that that is perpendicular to any one of our given sides. And as we're going to find out that the apothem, since it is a segment, has length to it, and the apothem is actually a critical component that's going to be used and to help us find the area of regular polygons. And when we approach the apothem from now on, we'll actually use the lowercase letter a to represent the length or measure of this of the apothem. Now we're going to talk about, before we get to our derivation of the area form of a regular polygon, we're going to talk about several properties that involve these two new segments, the circumradius and the apothem. Let's start with the apothem properties. So there's two assumptions we're going to make about the apothem, which these are actually true. The apothem has two properties to it. The first thing is this, that if you produce an apothem from the center to each segment or each side of your given regular polygon, all apothems created are equal in measure. So in our regular hexagon here, you see that I've illustrated an apothem from the center perpendicular to each one of the sides, and all 6 of those apothems are equal in length. And so given any regular polygon, if we produce all the apothems inside that given regular polygon, we're going to find that each of those apothems are equal in measure. So that's the first thing that we are going to find helpful in our area derivation, is that to know all of the apothems are the same length. The second thing that the apothem does is all apothems are bisectors of the sides. So the apothem is going to cut each side in half. And remember that all sides of a regular polygon are equal in length, which means if you cut equal things in half, you get equal halves, which is why in our diagram I've also denoted that all of the smaller segments that the apothem intersects, which are those sides, are all cut in half. Now I did make one mistake. Here's the typo I made. I forgot to put a hash mark on that one segment there. So let's go ahead and give that guy a hash mark. So the apothems, remember these two properties, all apothems produced in any given regular polygon are equal in measure, and they are bisectors of the sides. Not just actually any ordinary bisectors, they're actually perpendicular bisectors, if you notice, right? So actually kind of neat things happen there. There's also a property about the circumradius. Now, this property is not going to necessarily be needed to help us in our derivation, but it is going to be helpful when we move toward finding the area of regular polygons. So as we move towards finding the area of regular polygons, knowing that the circumradius actually, knowing this property of circumradii is actually helpful. And so this last property, before we move on to actually deriving our area formula and then using our area formula, is that the circumradii are angle bisectors. So if you were then to pick an angle of your regular polygon and produce the circumradius from the center to that angle you chose, it's going to cut that angle right in half. And so we can actually see some use of this later on. But some interesting things, happen, especially since all the angles inside of a regular polygon are equal in measure. Then it's appropriate for us to then mark all the halves equal, because if you cut equal things right in half, then all the halves are equal as well. So we've got all those angles marked with a single hash mark. Again, using our hexagon kind of as our platform, or kind of our template to use with these properties. So now what we're going to do is move on to actually deriving the area formula of a regular polygon. Now, not all regular polygons we're going to be given are going to be hexagons. So we have to then come up with a way to generalize the area of a given regular polygon. And what changes about a regular polygon is the number of sides. So you're going to see here in a moment that we're actually going to be using the number of sides to help us in our area derivation. Now, where I want to begin with this regular hexagon is I want to zoom in on one of the parts, or one of the components of the regular hexagon. I'm going to zoom in on where our apothem is drawn in. So remember, our apothem does two things. It's perpendicular to a side, it bisects the side, and we're also going to see that the length of the side is important. What I want to do is add a few things to my diagram here. I'm going to draw in two of the circumradii, which includes where our apothem is drawn in. Now, what you notice is that when those two circumradii are drawn in, it forms a polygon that we really like. This polygon is a triangle, and we're comfortable with triangles because we have seen part of our system how to find the area of any given triangle based on the given information. So the information we have at hand, we can actually find the area of this triangle, which our foundation for the area of triangle has always been this 1/2 base times height. Now take a look at the apothem. This is why I told you earlier the apothem is actually a critical value in finding the area of this. Because if you look at that triangle is formed, the apothem has a relationship to that triangle. The apothem is the altitude. It's the height of that triangle. So we know then that in our area formula for the triangle, we can replace the height with the measure of the apothem. And the apothem is perpendicular to the side, which means the side measure here is the base. So we know the base length is the side measure of our regular polygon. The height length is the length of the apothem. And with that, then, we can actually produce the area of that triangle as 1/2 the side length times the apothem. Now, you may be asking yourself, why is that important? I thought our goal was to find the area of the regular polygon, right? Not just this area of this triangle. But let's take this and find a way to then extrapolate this area of the triangle to find the area of the entire polygon based on the number of its sides. So here's the thing, okay? Here's the thing. We have let, in the past, this letter N represent the number of sides, okay? So number of sides of the regular polygon. Now, let me show you what we're going to do here. If I were to draw in another circumradius in this hexagon, what we form is another triangle. Now, there is something now provably true about these two triangles that we actually produced. Those two triangles are provably congruent. And because of that, the area of one is the same as the area of the other. But we don't have to stop there. We can continue to produce all of our circumradii in that regular hexagon. And that means we find that all of the triangles produced are in fact congruent, which means all 6 here have the same measure of area. Now, why is that important? Because let's look at for a pattern. There are 6 sides to a hexagon. Well, look how many triangles we were able to cut out of our regular hexagon with circumradii. We cut 6 triangles out of it. Okay, if I were to draw a pentagon, which has 5 sides, guess how many triangles we can cut out with those circumradii? 5 triangles. So a 5-sided shape had 5 triangles. This 6-sided shape had 6 triangles. What about a 10-sided shape? You're right, it's going to have 10 triangles. So not only is n represent the number of sides, but n also represents the number of triangles that we can decompose our regular polygon into. And since we know the area of that regular triangle, or we know the area of that triangle, which is 1/2 times the side length times the apothem, we can then generate our area of the regular polygon. So area of our regular polygon is equal to the area of our triangle, 1/2 the side length times the apothem, times the number of sides of that regular polygon. And there we have it. There is our area formula for a regular polygon. This is the one that I typically prefer. However, there is another kind of alteration of this area formula. So what I want to do is I want to show you the alteration and how we get there, and you can use any one of the two forms. They're going to get you the same thing. So what's happening here in this area derivation is that you'll notice that we're multiplying everything together. 1/2 times s times a times n, which essentially means we're multiplying the s, which represents the side measure of our polygon, times n, which is the number of sides. Now think about that for a second. S times n means something to us. If you took the number of sides and multiplied by the measure of each side, we actually produce something that we know we've already defined about our regular polygon, or really any polygon, and that is the perimeter. Think about that. If you have n number of sides and you multiply it by the measure of each of those sides, you actually calculate the perimeter of that polygon, which means what we can do is alter this equation just a bit. We can say the area of our regular polygon is then still the 1/2, but take the s and the n and replace it with p, the perimeter. So it's at 1/2 times p times the apothem. And that is an altered form of our regular polygon. So both of these will do the same thing. They still give us the area of the regular polygon. However, typical textbooks will show the 1/2 perimeter times apothem because it's in a more, I guess, simplified form. However, I prefer using the first one because it shows us, hey, It's based on our area formula of a triangle, and then n represents the number of sides. So simply find the area of a triangle, multiply that by n, and you've got yourself the area of your regular polygon. So what we're going to do in these last several slides is actually do some examples of using our area formula and using some of the properties that we've seen with the apothem and with the circumradius to actually find the area of our regular polygon. Now, what I'm going to show you is that there are 3 different types of ways you can actually tackle finding the area of a given regular polygon. And what I'm also going to do is be changing the shape of our regular polygon to show you that even though the shape changes, our approach is going to be the same. So what we're going to start with is, since we've seen our hexagon used in our examples as our template, let's go ahead and tackle our first example as using a regular hexagon. Now, we're going to start with the case in which I'm going to give you, or you are given, the length of the apothem first. So if we're given a regular polygon in which we're given the length of the apothem, we can find the area of this with the given length of the apothem. So we're told the apothem length is a length of 12. Now remember, I can draw the apothem really in anywhere, and the apothem length is going to be the same measure. So what I'm going to do is I'm going to draw in apothem length here, just so I can see it work better out for us. So the apothem right here has a length of 12. Now remember what our goal is. Our goal is to find the area of this triangle and then multiply it by the number of sides. Well, in order to find the area of a triangle, we already have the apothem, but we need one other critical value. We need to know the side length of our regular polygon. And once we have the apothem and our side length, we can find its area. So let me show you how we're going to go about finding the area of this triangle. Where we start is something where it seems a little bit unconventional, but I'm going to show you that this first step is going to take us into the place we need to go. See, if I were to draw in every single circumradius, right, inside of this regular hexagon, let me draw another circumradius here. Let me show you what happens. There is an angle formed between the 2 circumradii. Well, as it turns out, we can find the measure of that angle, and here's why. One full rotation, so let me kind of do like a quick, just one full rotation about our center point there is 360 degrees. But as it turns out, all the circumradii cut that 360 degrees into into the number of equally measured angles. So we take first 360 degrees, and since this is a hexagon, we divide it by 6, which means each of those angles between our circumradii measure 60 degrees. So this angle formed between these 2 are 60. But as it turns out, since our circumradii are all equal in length, the apothem is actually not just the altitude, but the apothem is an angle bisector. Because of our circumradii being equal length, these triangles that are produced are isosceles, which means these angles here are being cut in half by the apothem. So if the entire angle is 60 degrees between circumradius and the other circumradius, then it gets cut in half. What I'm finding here is that this angle measure is 30 degrees. Now, what I'm going to do is, with this triangle that's formed, right, we're trying to find the area of this triangle, we can then zoom in on this triangle right here. I'm going to bold it for us, okay? So let me bold this triangle. And that's really going to be the goal in every single case, is we're going to use this triangle here to help us find any missing measure. So I'm going to zoom in on that triangle. The apothem is a length of 12. This would be our circumradius. And remember that the apothem cuts the side measure in half, which means this length would be half of our side measure. We want to find that side measure. And as it turns out, because we're taking the 60 degrees and cutting it in half with our apothem, this angle measure that we find here is 30 degrees. So what do we have for ourselves? What we have for ourselves here is a right triangle with a 30-degree angle in it, which means we can think of this 2 ways. The first way is we could use trigonometry then to find our missing side measure. However, since we are dealing with our special angle, we can use special right triangles. The hexagon is going to be really nice to us every single time because it will always produce these 30, 60, 90 right triangles. Same goes for the equilateral triangle and the square. Those also produce really nice special right triangles for us. We'll see some examples here in just a minute where there are not special right triangles. In other words, anyway, let's get back to on hand. We need to find the side measure of this regular polygon. So what I'm looking for is to find the side measure of the side S. So if I know that the opposite side is my short leg, right? So half S is the short leg. I need to go from the long leg, which is this side 12, to the short leg. How do I get there? Remember, when I go from the long leg to the short leg, is I need to divide by √3. So my half of the side length is equal to 12 divided by √3. Let's solve for S. I'm going to simplify. 12 divided by √3 is actually 4√3. And then I need to double that because I want to multiply both sides by 2. So the S, the side length, is really now 8√3. With our apothem that was given, with our side length we just found, and with knowing the number of sides of this regular polygon, we can find the area of it. So the area of our regular polygon, I like to use this method, is 1/2 the side length times the apothem times the number of sides. So our 1/2 of our side length, which is 8√3, times our apothem length, which is 12, times the number of sides our regular polygon has, which is 6. What we can do with this then is we can actually multiply our outside numbers together. We do have that √3 is going to stick on the very end, and we get our area of this regular polygon. So 1/2 times 8 times 12 times 6 gives us 288. We slap that √3 on the very end of it, and there is the area of this regular polygon. Using what we know to be true, we found the length of we were given the length of our apothem, we found the length of the side, and that's really going to be the goal in each case, is depending on what we're given, we need to make sure we have both the apothem length and the side length. Let's take a look at our next example. We're going to go from a hexagon to an octagon now, okay? But the process we just did is going to be similar, okay? We do have to take one little bit of a detour just because the nature of the angles that we get here are not going to be nice to us. So we're going to have to then take a slight detour and to find a missing segment measure. So we're given the length of the side is 16. So we've got the side length S, but we're missing the length of the apothem. So now we have to dig a little bit to find the length of the apothem. What I'm going to do first is I'm just going to go ahead and roughly draw in where my center is, and I'm going to produce an apothem inside of there. So there's my apothem. Next thing I do, remember, is I want to find the area of this triangle here, okay? And how I find that area is using the apothem and side length. Now, I know that the apothem cuts the side length in half, which means it takes my entire length of 16 and it cuts into 8 and 8. But our main focus is on just half of this triangle that's formed because it's a right triangle. Now, I'm going to zoom in just for a moment. I'm going to draw that right triangle, and we're going to begin to find some information about this right triangle that I've highlighted over here. We know that this side down here is a length of 8, and our goal is to find the length of the apothem. How do we get there? Well, remember the very first thing we did with hexagon was we said that one full rotation about our center is 360 degrees. And that gets cut into the number of sides we have of equally measured angles, right? So if I were drawing every single circumradius, the angle between the two circumradii there, we can find that by taking simply 360 divided by the number of sides, which in this case is 8. So we get the angle measure between the circumradii to be 45 degrees. But the apothem cuts that in half, right? It cuts that angle right in half. In other words, the angle we're looking for here, we can take that 45 and divide that by 2, and so we know the angle measure of that angle, we find it to be 22.5 degrees. Now, here's the problem. That's not one of our nice angles, right? We're looking for a 30 or a 45 or a 60. So what do we do with 22.5? We're going to have to use trigonometry. So now think about what we have. So 22.5 degrees, the opposite angle is our side 8. The adjacent side is our side, which is our apothem. We have to use trigonometry here, so we're going to be using tangent. So tangent of our angle is equal to the opposite over the adjacent. Let's plug in what we know. Tangent of our angle, which is 22.5, is equal to the apothem 8 over the circumradius A. Well, the tangent of 22.5 we can turn into a ratio. It turns into 0.4142. So I'm going to go at least 4 decimal places for accuracy, and you'll see I won't round until the very end. And then I have that 8 over A, Well, remember what our algebraic trig was. We can just swap that out. And what we're doing there is we're solving for the length of our apothem. So we get the apothem is 8 divided by this 0.4142. And we get then an approximation of our apothem to roughly be 19.3143. Now that we have the measure of our apothem and we were given the length of our side, we can find the area of this regular polygon. So the area is 1/2 the side length times the apothem times the number of sides. So we have 1/2 the side length, which is 16, the apothem, which we found to be 19.3143, times the number of sides we've got, which is 8. We multiply that all together, and we get roughly 1,236.1, and that is our area of our regular octagon there. So pretty cool. Again, we had to take a kind of slight detour of using trigonometry, so not this nice fast-paced where we end up with a special right triangle. But we still are able to find the missing measures we need because we were given the side, we're given the apothem. So this is the second case you're going to find. So the first case is you could be given the apothem, which means you need to use then your triangles to find the side, or you could be given the side and you can use it to find the apothem. But there's one more case, which is the trickiest case, and that is if you're given circumradius. So with the circumradius, you're missing both the apothem and the side length, which means we got to find two measures in this. And so with the little extra work, it is a little bit daunting, but we're going to be able to get through it using the same process. So the circumradius is a measure of 3, and we know we need to find both the side length and the apothem length to help us find the area of this regular pentagon. So where I'm going to start is I'm going to draw in some extra circumradii, and I'm going to go ahead and draw in the length of our apothem. So our apothem is the length of A. Our circumradius is length of 3. Now remember what we do is our main focus, I'm going to highlight this, is the main focus is on this bolded triangle. Because from that bolded triangle, we can actually relate the three sides together using trigonometry. So I'm going to zoom in on that triangle. I'm going to zoom in on that triangle there with the side length as the apothem. The circumradius is a length of 3. And remember, what happens is the apothem cuts our side length in half, so the whole side is S, which means this is going to be half the length of our side length, half of S. Now, the next goal then is to find out what this angle measure is here at the top. So how do we do that? Well, remember the one full rotation about the center of our center, or one full rotation about the center. There are going to be, if we draw in all the circumradii, there are going to be 5 triangles, which means we can figure out the measure between the circumradii by taking 360 divided by the number of sides, and then each one of those angles measures 72 degrees. But the apothem cuts that angle in half, right? So apothem cuts that angle in half, which means we know the angle measure here is going to be 36 degrees. Now we have that angle measure, we've got an acute angle measure, and we have a side measure. We're going to use trigonometry to find the missing measure of our apothem and the missing measure of our side length. Let's go ahead and do the side length first. It's the one that requires a little bit more work to it. So we'll do the side length first. So the side length, this half side length, is the opposite side, and our 3 is our hypotenuse, which we'll go ahead and say the apothem is the adjacent side. So we're going to find our opposite side first. So the sine function is going to be used. Sine of our angle, 36 degrees, is equal to our opposite side, which is 1/2 S, over our hypotenuse, which is the length of 3. We're going to then solve for the measure of S here. So where I like to start there is simply turning our sine of 36 degrees into a ratio. So it's 0.5878 is our ratio there, equals 1/2 the side length over 3. Now I'm going to multiply both sides by 3, and when I do that, I get on the left-hand side 1.7634, and then on the right-hand side I'm left with this 1/2 times S. Then I can take that value, multiply both sides by 2 to get our side measure, and I'm going to keep at least 4 decimal places here, to be roughly 3.5268. So there's one of our missing values, the side length. Now we need to find the length of our apothem, which length of our apothem is not going to be too bad. It's the adjacent side, and we have our hypotenuse, which means we're going to use cosine. So cosine of our angle is equal to the adjacent side apothem over our hypotenuse length of 3. Our cosine of 36, we turn that into a ratio, 0.8090 is equal to then the apothem over 3. Multiply both sides by 3, and we get the apothem length to be roughly 2.4270. Now we have both of our missing measures. So you see, we had to dig a little bit deeper. We had to find both of our things we needed: the side length of our side length of our regular polygon and the apothem of our regular polygon. Now we can use our area formula. So the area formula is 1/2 the side length times the apothem times the number of sides. So we have 1/2 the side length, with this 3.5268, times our apothem, 2.4270, times the number of sides. This is a pentagon, has 5 sides. Oops, 5 sides. And we multiply that all the way through. And I'm going to go ahead and round it here in this last step. So it's approximately the area of 21.4. And there we have it, the area of our regular pentagon there. So you're going to find that on your homework assignment, you're going to run in each of these 3 cases. One in which I give you the apothem length, others where I give you the side length, and others where I give you the circumradius. And so depending on what you're given, you're going to have to dig to find the other measures. And so remember the process, right? Follow what I did. First, I figured out the number of sides, right? So I counted the number of sides. I thought about then the relationship between the apothem, the circumradius, and half the side forms that triangle, and I'm looking for information about that triangle. So sometimes you're given the circumradius, the side measure, or the apothem, which means you already have a side measure of that given triangle. And then you got to find an acute angle measure. And how we do that is, remember, you go one full rotation about the center, which is 360, divided by the number of sides, gives you the measure of the gives you a measure of that central angle. But that angle gets then cut in half by the apothem, and that's the acute angle measure that's going to go in that right triangle. And we saw that in every single one of these examples here we did, and that's the process you're going to take going through each of the problems you find on your homework assignment. So we've come to the end of our lesson here with our areas of regular polygons. If you do have any questions on the homework assignment, please don't hesitate to email me. With that, be good and do good.